Welcome to the review for the third quiz of differential equations, Math 245. We'll start with the exercises. For problems 2 to 5, let's use A and B given. Okay, so select all the bubbles to all answers that apply about the determinant of A. They're saying the determinant of A is equal to 4. Well, let's see if that is true. The determinant of A is 2 times 3, which is 6, minus 2, which indeed is 4. So I would definitely bubble this one. Now, transformation A increases the size of areas in the plane. So a determinant equal to 4 means that each square of a matrix of a grid to which the transformation A is applied is increased by a factor of 4. So yes, the transformation A increases the size. Now you might ask yourself, well, how do you decrease the size? Well, if the transformation matrix has a determinant that is between 0 and 1, then that would mean that it decreases the size of each shape and the area that is contained in the grid that it's transforming. Now, the determinant of A cannot be 0 because we already established that the determinant of A is 4. And it cannot decrease because we already said that it increases it by a factor of 4. So this is the answer to problem A, problem 2. Now let's go to problem 3. Select all the bubbles to all answers that apply about the inverse of A. Well, let's see. If A times X is equal V, then X is equal to A inverse times V. Well, let's think about this for a second. We know that A times the A inverse, assuming that it has an inverse, is equal to the identity matrix. So if we have A times X equal to V, and we assume that these are both vectors, and that the multiplication is defined for these two guys because they have dimensions that work out. If I multiply, let's see, I made a mistake here. I can write it like this, but I like to write the inverse matrix on this side. So if I write the inverse matrix here and here, then here I would get the identity matrix times X and the inverse of A times V. Indeed, we don't have to write the identity matrix because it really doesn't alter our vector. And so we can say that this is actually true. And that's what we have over here. Excuse me. So we can say that that is true. And they want us to select all bubbles that apply. And this one definitely applies. So I'll select this bubble. And then let's see if the matrix A is equal to the inverse of A. Well, to do that, we'd have to calculate the inverse of A. So I'll calculate the inverse of A right here with the adjoint method. The inverse of A is going to be 1 over the determinant of A, which we already have, is 4, times the adjoint of A, where the adjoint of A is the matrix C11, C12 with the cofactor expansion. This transposed. So C11 is 3. because I look at this and I eliminate the rows and column that correspond to a row of 1 and a column of 1. And what remains is the submatrix 3. Then I can say that C12, I notice that the subscript add up to an odd number, so it's going to have a negative in front, and this one's going to be -1. So this is going to be 1. Then C21, this is going to be -2, and I notice it has to have a negative in front. And then C22 is going to be 2. Okay, so now I can say that the adjoint of A is equal to 3, 1, 2, because the negatives cancel out, and 2. And then I need to transpose it. So transposing it, the diagonal will stay the same, and we'll have this. Now, let's look at what A was. And do you think that this is equal to the matrix? Well, we're not done yet. Now, the A inverse, if we divide by the determinant, which is 4, and we multiply by the adjoint, we're going to get 3/4, 1/2, 1/4, and 1/2. This is definitely different than our original A matrix. So we don't have that A is equal to the inverse of A. So we can cancel this one out. A inverse is a 2x2 matrix. This one's a 2x2, and the inverse retains the dimensions. Indeed, this is also a 2x2. So this one actually applies. And so I can bubble it. And then this one, if AX is equal to V, then X is equal to V A minus 1. Well, let's see if that is the same logic that we had before, but now the A is on the right. So let's apply the inverse matrix on the right. Now the problem with this is that yes, we get an I on the left because they'll have the same dimensions. But on the right, say this is a vector that has dimensions A and B, so 2 by 1, and this is a 2 by 2, or whatever. This is a 2 by 1, this is a 2 by 2, and we would get that the multiplication isn't defined. So you have to be careful here. It depends on what V is. If V is representing a vector, then this would not apply. But they didn't really specify in here. So I guess we could make an argument that if V is a 2 by 2, then this would be true. Now, for lambda 1 equals 1 and V1 equals 2, 1, what applies? Let's see. Let's see, if we have A times V1, and I multiply lambda times V1, that should be equal. Well, let's see, our A is, so we'll do E over here. Our A is this matrix, 2, -2, -1, and 3. 2, -1, -2, and 3. And if I multiply this matrix by the vector V, which is the vector 2, 1, do I just get 1 times, and I should probably avoid this because it might be confused by a dot product, 2 and 1. Do I get this? Well, let's see. We get a 4 minus 2 and a negative 2 plus 3. Is that equal to 2 and 1? Well, a 4 minus 2 is equal to 2. Negative 2 plus 3 is 1. So we indeed do get what they said. So this one definitely applies. And since it applies, we can bubble it in right here. Now, L1 is the only eigenvalue of A. Now, let's see if that is true or not. Let's find the eigenvalues. So this is E, F, I believe. This is going to be 2, negative 2, negative 1, and 3. And we're going to want to subtract the lambda here and find the determinant of this. Let's see what we get. What we get, I'm going to take out a negative sign and factor it out from both of these. And then we have minus 2. So let's see. The negative signs will cancel out. Here I'm going to have L squared minus 5 lambda plus 6 minus 2, which is equal to lambda squared minus 5 lambda plus 4, and that all has to be equal to 0. Now we can factor that into lambda minus 4 and lambda minus 1 equals 0. So then we have lambda 1 is equal to 1 and lambda 2 is equal to 4. So there's actually 2 eigenvalues. And because of that, this does not apply. So we won't bubble it. Let's look now at the transformation A moves V1 of F. So where is F? Off its span. Oh, sorry. This is off of its span. Okay. Well, the transformation A actually only makes V a scalar multiple of what it originally was. And in this particular case, it doesn't even scale it. It just stays the same, which means that this is not true. It doesn't move V1 off of its span. V1 is 2, 1. So V1 is here. After the transformation, V1 is still here. So it's still in its span, which is this line. So that one's also not true. Let me do it in red. And now they're saying the absolute value of the left-hand side of this is equal to the absolute value of the right-hand side. Well, for that one, we can look at this. Is the absolute value of, so let's say this is H. Is the absolute value of this equal to the absolute value of this? Well, how do you take the absolute value of a matrix? I'm not sure. However, these are particular matrices. These are vector matrices. So we can take the square root of the square of 2 and 1, which is going to be 5. And this is also going to be 5. And those indeed are the same. So we can say that this one does apply. We can say that this one does apply. Okay, and now let's look at the last one from this section where you're using the same 2 matrices. And now they're telling you what is the determinant of the product of A times B. Well, to know the product of A times B, and then find the determinant, we'd have to compute it. And we have that this is a 2 by 2 and this is a 3 by 2 because we count the rows first. So the product would actually not be defined. So definitely we could not calculate the determinant. And so these are not true because you would not get a product out of it. And this is true. It does not exist. Okay. Obviously, all of these things can be done quite faster in MATLAB, but it's a good idea to have an understanding of where they're coming from. So let me just show you what we did. 2, we calculated the determinant. B, we interpreted what that means. 4, we interpreted whether the statement in A is true, and it is true assuming that the multiplication is defined. And the inverse of a matrix, it has the same dimensions. Well, yes, because only a square matrix can be inverted, and so the inverse will still have a 2 by 2 because the rows will become columns, and if there were 2 rows, there will be 2 columns, and the columns, which were 2, will become rows. So it'll stay with the same size. Then for number 4, we looked at which statement is true. I think I misinterpreted this one. I could not select 2 of them. So I wonder which one of these 2 is correct. I think this one's definitely true. And AV1, we did AV1, and we see that it is indeed correct. That was E, which is right here. And we have H, and it also seems that H is correct. So this one we might want to check, ask someone. And then AB does not exist because the dimensions are different. And these 2 have to be the same in order for the operation to be defined. Had it been BA, then it would have been okay. All right, I'll keep going in a different video.